This lesson is on polynomials, and the first thing I want you to do is remember what our toolbox functions y equals x squared and y equals x cubed look like. So x squared is a parabola, it's kind of a U shape, and then x cubed is the little curve shape that goes through 0, 0. And those are your basic shapes that we're going to be referencing in this lesson. In general, if a polynomial has an even power, like this x squared, x to the fourth, x to the sixth, and so on, even powers are going to have this U kind of parabola or a W looking shape, U or a W look to them. If they're facing up, they're going to start and end up. If they're facing down, they're going to start and end down. If it is one of these graphs, again, this U and W shape I could be talking about. The W shape can look, something like this, or the middle can go higher. One of these valleys could be higher or lower than the other, but it will have a look to it that resembles a W. And again, the U shape, the parabola you're familiar with, it could be skinny, it could be fat, it could be facing up, it could be facing down. It's just variations, but both ends go up or both ends go down is what we're trying to get at here. If it has an odd power, like x to the third, x to the fifth, x to the seventh, and so on, odd powers are going to typically, like the x cubed graph, start down and end up, or if it's a negative version, it's going to start up and end down. So like we could have the normal looking x cubed but with some hills and valleys in the middle, something like that. It starts down, it ends up, because we read our graphs left to right. Or if it was a negative version, the second thing that I'm talking about, it could come down like this, start high and end low. And again, the middle might have some hills or valleys in there, like this one. That all depends on what's going on with some other things on the polynomial, but that highest power is going to determine that shape. The leading coefficient test. The leading coefficient is the number that's in front of the highest power of x when you line it all up. If that front number is positive, then the graph is going to look like the original. In other words, if it's an even, it's going to face up. If it is an odd, it's going to resemble the x cubed. If the front number is negative, it will be flipped, and it will look the opposite way. And we've worked with having a negative in front, so it's just that same relationship that we have talked about before. One of the types of problems that you're going to have today is I'm going to ask you to describe the end behavior, and that end behavior is that up and down ending and starting that we're talking about. And the way they write it, they're going to write x goes to infinity or x goes to negative infinity. That's kind of like a mathematical sentence. If they say x goes to the infinity, they're talking about the right end of the graph. And if they talk about x going to negative infinity, they're talking about the left side of the graph. And you're going to answer with what y is doing. What is y approaching? Positive infinity or negative infinity? Is it going up or is it going down? So, for example, and we're going to use that leading coefficient test here. We're not going to type these in our calculator. The first one, we have this y equals x cubed. I don't care about all this other stuff. The fact that it is y equals x cubed and the coefficient here is positive means it's going to face up or face like a normal cubic graph. The left end is going to go down, the right end is going to go up. Now, all this other stuff will affect what happens in the middle, but we're not looking at that right now. We're looking at the end behavior. So we're going to answer what's happening as x goes to infinity and what's happening as x goes to negative infinity. So if you're on this graph, the right end is going up. So as x goes to infinity, y goes to infinity because it goes up. And then the negative infinity, the left end, we're looking at that on the graph, what's happening there, our y's are going down. So as x goes to negative infinity, our y's go to negative infinity. And again, that is our basic odd shape. So let's move on. We have a negative coefficient in front of something with an odd power, which means that graph is going to be flipped. It's going to be odd shaped but flipped. So again, I'm going to start by writing x goes to infinity and x goes to negative infinity. This x goes to infinity is the right end, so the right side of this graph is now here. And what's happening to its y values? They're going down. So y is going to go to negative infinity. Then as x goes to negative infinity, what's happening? That's the left side of the graph. We're going to look at that. That arrow is pointing up. Our y's are going up to positive infinity. Alright, this will be a good time to pause and look at 3 and 4 if you can do that. See what you think. And if not, I'm going to continue on. First of all, 3 is an even-shaped graph and it's positive coefficient, so it's going to be face up. Could have some other stuff going on in here, but the ends are facing up. So as x goes to infinity, looking at the right end, y is going to go to infinity. It's going to go up. Then as x goes to negative infinity, looking at the left end, it's going to go up. Y is also going to go to infinity on that end. Number 4, we have a negative even-powered graph, so that's going to be some U-shape facing down. So the right and the left ends are both going to go to negative infinity because they're both going down. So I write that as x goes to infinity, y goes to negative infinity, and as x goes to negative infinity, y goes to negative infinity. And so that's our even graphs. The next thing that we're going to be doing today is finding the zeros of a polynomial. Zeros are another word for x-intercepts, where we're crossing the x-axis. And the number of zeros that we have should match the highest power of x. So again, we're looking at that highest power of x to tell us something, and it tells us how many times that we should cross the x-axis, or at least how many zeros we have. Now, the thing is, not all of those are going to cross the x-axis. You've seen parabolas that don't cross the x-axis at all, and that's because there are real answers, which are places that we cross the x-axis, but there are also what's called complex or imaginary answers. And we're going to deal with those more later. Those are the I's that you probably talked about in a previous math class. So those can be answers. Today we're going to focus on the real answers. So here's an example. If I look at this and I graph this on my calculator, it's going to look something like this. And if you calculate the zeros, well, first of all, one, you can notice that there are 3 zeros here. You have it crossing here, here, and here. And you can calculate those using the menu, second calculate menu, and get negative 1.86, negative 0.25, and 2.34. So you can get those using your calculator, and hopefully you remember how to do that from a previous class. But since we only crossed 3 times and the highest power of our x is this 5, we've got a problem. So what's going on? We have 3 real solutions, or 3 real zeros. Those are the negative 1.86, the negative 0.25, and the 2.34, where that graph is actually crossing the x-axis. That leaves us with 2 imaginary solutions, and we're not going to go over how to find those in today's lesson, but we will in a future lesson. So just know that obviously we see 3 real, it's supposed to have 5, so 2 of them have to be imaginary solutions. Now in that example you had to graph on the calculator because those were some decimals, but sometimes they ask you to find these algebraically, and you can actually factor and figure them out. What you do is you set the polynomial equal to 0, because we are trying to find these zeros, and then you factor. In this case, I have a GCF of x, so I take an x out of everything, and then I can factor what's left is a quadratic. I can factor that into 2 parentheses. So if I use my little x factor, I've got 1 and -2, so it's -2 and -1, so that'll be -2 times +1. So x minus 2 and x plus 1. And then I can find those 3 real zeros by setting equal. So x will equal 0, x minus 2 will equal 0, and x plus 1 will equal 0. So I have this as an answer. If I add the 2, I get this as an answer. And if I subtract the 1, I get -1 as an answer. The line right here, this is called the factors, the linear factors. Technically this is x minus 0, but if it's 0, then obviously we don't write it. X minus 2 is a factor and x plus 1 is a factor. Then our zeros are 0, 2, and -1. Notice that you have opposite signs. So if it was x minus 2 here, it's a +2 as the 0. If it's plus 1, it's a -1 as the 0. So the factor will have the opposite sign of the 0. And that's going to help us in a little bit. I did find 3 answers here, and I was supposed to find 3 because that highest power of this was 3. So everything here was a real answer. On our next example, again, I'm going to start by setting that equal to 0. And I'm going to factor again. I have a GCF again in this case. I can pick positive or -2. I'm going to pick the -2. And they both have x squared, so take that out. And that will leave me with x squared minus 1. And it's minus because when you take a negative out, it changes the signs. That first piece was negative, now it's positive. The second piece was positive, now it's negative. I'm ready to set things equal to 0, so 0 will equal -2x squared, and 0 will equal x squared minus 1. I could actually factor that more, and probably that would be a good idea. So let me back up for a second before I do that and say 0 will equal -x squared and x minus 1, x plus 1, because that was perfect squares. You can still solve it and just remember to take the square root as positive and negative answers, but if it does factor, that helps you remember that. So now I can set these equal to 0. -2x squared equal to 0, x minus 1 equal to 0, and x plus 1 equal to 0. Here, if I divide anything by -2, then, or 0 by -2, it's still 0. And if I take the square root of 0, it's still 0. If I add 1, I get x equals 1. And if I subtract 1, I get x equals -1. And again, you'll notice we have the opposite signs between our factors and our zeros. Now, we're supposed to have 4 answers and I only have 3. What's happening? It's not that we have an imaginary one. It's that when you take a square root, like I was saying, you're supposed to use the positive and negative answers, but 0 is neither positive nor negative. So technically this 0 counts twice, and I'm going to address that more in just a minute. So I do have 4 answers here because a square root will give us 2 answers. So I will explain that in just a moment. Okay, and then finally example 7, if you look at it and you set it equal to 0, you kind of get stuck because it doesn't factor. So today what I want you to do is, if it doesn't factor, then I want you to graph it like we were looking at that original example. Graph it in your calculator and calculate, using the calculate menu, the zeros. This one is similar looking to that example. Something like this. It's going to cross in 3 places. If you calculate those, it'd be -1.73, -0.45, and 1.73. And I encourage you not to just take my word for it. Actually graph it and calculate those to make sure you remember how to do that. So since there's supposed to be 5 answers and I have 3, that means I have 2 imaginary answers and the 3 real answers that I just found, which would be negative 1.73, negative 0.45, and 1.73. So that's what I want you to get today. Okay, the graph information you should know. There's this thing called multiplicity, and that is how many times an answer counts. Just like in that example 6, we got that 0 twice, and that 0 counts twice. What does that mean? Well, if a graph has a 0, and that graph just goes straight through, that counts once. That would be a multiplicity of 1, and we don't normally write multiplicity 1 on things. If we have the x-axis here, and our graph is either on this side or this side and bounces off, the graph bounces off at that 0. Doesn't it touches it, but it comes back the other way. That answer is going to count twice. So if we were to look at that graph from number 6, it would bounce off at 0 like this. And again, this could be face up or face down, but it's going to hit the axis and come back, kind of like a boomerang. Now, they can count more, and the way that you're going to see that on a graph is it can bounce off and count more by being, it'll look extra flat at that point. Or if it is counting like 3 or 5, this is an even amount obviously, and if it counts 3, 5, 7, something like that, an odd amount, it's going to still go through, but it's going to flatten out at that point. So I'm just going to put they can count more times, but if it's an even, it will bounce off. If it's an odd amount, it will an odd, even multiplicity and an odd multiplicity. Even multiplicity will bounce off, odd multiplicity will still go through, they just get flat. Okay, the last thing that you're going to work with today is being able to write equations given the zeros. And here I'm incorporating that multiplicity into it. So what this means is 3 multiplicity 2. That means I get 3 counting twice, and the graph, if I had to graph it, which I'm not at the moment, would bounce off at 3. I have negative 1/2 multiplicity 1, so my zeros are 3, 3, and negative 1/2 if I had solved it out. So what we're going to do is back those up into factors, and we're going to get the polynomial that we would have started with. So it's kind of like undoing the factoring. So if 3 is a 0, then x minus 3 would be the factor. And we have 2 of those. Now, the negative 1/2 you want to think of kind of like we do that x factor factoring. If negative 1/2 is a 0, I'm going to come over here and do my scratch work, then x plus 1/2 is my factor, but we swing that 2 to the front just like when we use the x factor. So 2x plus 1. So there is my polynomial with the zeros of 3, 3, and negative 1/2. I want to work that out. You can only multiply 2 things at once. So I'm going to start by multiplying these 2 and put their answer here. I'm just going to bring down the 2x plus 1. So x times x is x squared. X times negative 3 is negative 3x. Negative 3 times x is negative 3x, and negative 3 times negative 3 is positive 9. So then I want to triple distribute. So that means I'm going to take the 2x and multiply it by everything in here, and the 1 I'm multiplying by everything in here. Before I do that, I'm going to go ahead and combine these two negative 3x's and make that negative 6x, just so I have a little less to deal with. So take the negative 2x and multiply it in. So I'm going to get, positive 2x. 2x times x squared would be 2x cubed. 2x times negative 6 is negative 12x squared. And 2x times 9 is 18x. Then I'm going to do the 1 times everything. So 1 times x squared is x squared. 1 times negative 6x is negative 6x. And 1 times 9 is 9. So 2x squared, you can combine like terms, so I get negative 11x squared. Excuse me, that was a 2x cubed. Negative 11x squared. I have 18x minus 6x is 12x, and then plus 9. So this is the polynomial that would have factored to this and given us those zeros. It's kind of like working backwards. All right, we have two more examples. This one has square roots in it, and whenever you have one thing with a square root, you will have the conjugate also, whether or not they write that down. So if they had just given you the 3 and the 2 plus the square root of 11, you would also know that you would use the 2 minus the square root of 11. I don't know that they'll bring that up, but if they do, just remember to write that down. So if I don't have any multiplicities here, so I don't have to worry about that. I just have to back these up and multiply. So I have x minus 3. What happens here is you distribute that, you do the opposite sign of both. So x, this is a positive 2, so I'll put minus 2. This is a positive square root of 11, so I'll put minus square root of 11. And then the same thing here. X, this is a positive 2, so I put minus 2. This is a negative square root of 11, so I put plus square root of 11. And I'm going to multiply those two nasty ones first. So x times x is x squared. X times negative 2 is negative 2x. X times the square root of 11 is x square root of 11. Negative 2 times x is negative 2x. Negative 2 times negative 2 is positive 4, and negative 2 times 11 is negative 2 square root of 11. Then negative square root of 11 times x is negative x square root of 11. Negative square root of 11 times negative 2 is a positive 2 square root of 11, and negative square root of 11 times 11 is a negative 11. Then before I distribute the x minus 3 in, I'm going to combine like terms because things are nasty. So I have the x squared, I have negative 2x and negative 2x to make negative 4x. The positive x squared of 11 and the negative x squared of 11 will cancel. Same thing with the negative 2 squared of 11 and the positive 2 squared of 11. That leaves me with 4 minus 11, which is a negative 7. Then I can distribute and things will be easier. So x times x squared, x times negative 4x, and x times negative 7, then negative 3. Negative 3 times x squared, negative 3 times negative 4x, and negative 3 times negative 7. So I have x cubed. The x squareds can be combined. The x's can be combined. And I bring down the plus 21. So here's the polynomial that would have factored like this and would have these zeros. Okay, our last example, we have a 0 of 0, the 3/4 and the negative 2. And the 0, if you'll look back at that previous example where we had that as an answer, it came from just a plain x. We don't write x plus 0 or x minus 0. We just have x. I mean, you can put x plus 0 or x minus 0, but then you're just going to have to simplify. The 3/4, again, is like saying x minus 3/4, and you swing the 4 to the front. So this is 4x minus 3. And then the negative 2 came from an x plus 2. So I'm going to bring the x down, and I'm going to FOIL here. So I get 4x squared plus 8x minus 3x minus 6. I'm going to combine like terms. And 8 minus 3 is 5, so 5x. And then I distribute the x. So I get 4x cubed plus 5x squared minus 6x. And that concludes this lesson.